Exercise 1E, composite functions. Today we're learning about the nature of composite functions and requirements for them to exist. What you need to be able to do is find the rule of a composite function, f of g and g of f, understand the theory of defined composite functions, and be able to restrict the domain in order for a composite function to be defined. So this is a little bit of a depiction about what we're kind of doing today. So we're looking at functions within functions. If we have a function f of x, which is pizza, g of x, which is pineapple, we can have f of g of x, where the pineapple is in the pizza. Really, it's on in a literal sense, but mathematically we say it goes in, whereas g of f of x is the other way around, where the pizza is on the pineapple. So that there are pineapple composite pizza functions. So that's kind of what we're learning about today. Now, before we get into the actual examples, I just thought we'd kind of talk about and break down the concepts a little bit more. We're used to looking at functions like this, 3x plus 2 all squared, just as a function as it is, but we're going to kind of try to break it down today, looking at all the different layers instead. So the first question is, what does this function tell us to do for a given value of x? And if you can see, there's kind of like two steps. The first step is this inside part. So first of all, what we're going to do is we'll do the 3x plus 2. And then the second part is whatever I get from that, we're going to go ahead and square it. So if I were to call this inside part function of x, so that's the first thing I'm going to do, then for the second part, all I have to do is square whatever I get out of that function there, f of x all squared. And we can call that g of x. Or rather, to be formal, it would be g of f of x because the input is f of x. So that's what our notation is for composite functions. And the idea is that from today, we're going to start looking at the different layers of functions rather than just a function as it is. So the question then says, complete this process for x is equal to 3. So we said the first part is our f of x part. So we are going to insert 3 into that. That'll give me 11. And then the second part is to do g of f of x. So g of f of x is where I'm going to go ahead and square the function. So that'll be 11 squared, which is 121. There's two layers to it. A visual depiction of this is this over here. So our f machine, which is the inside function, g machine, that's our outside function. So think of this as f of x, g of x. We have a certain number that we're going to input. In this case, we're putting in the number 3. That goes into here, and we come out with the value of 11. But it doesn't stop there. That value 11, which we've pulled out, now becomes our input into the g machine. And that's where we get our final value. So there's like two layers to it. The input becomes an output, but that output becomes the new input. And so that's the idea of composite functions overall. So composition of two functions occur when the output of one function becomes the input of the second function or the outside function. So let f of x equal to x squared, let g of x equals to 1 minus 2x, then we can compose two composite functions. We have fog, which would be f of g of x. That means I'm inserting g of x into the function of f. And we also have gof, which is over here. That's where I would insert f of x into the function of x. Now, very simply, how do you do this? Wherever you see x, all you need to do is just input that in. So instead of putting in a certain value, you put in the whole function. And this page here is just to kind of practice that. So it's literally like normal substitution. So we have the function f of x. If we were to just substitute very simple values that we're used to, f of 2 means I'll put 2 into there. So that'll be 4 squared is 16. If we have a, f of a, instead, this will just be a plus 2 all squared. If we need to substitute a plus 2, so wherever I see x, I'm going to write a plus 2. That'll give me a plus 4 all squared. And if I were to substitute a whole other function, instead of writing x, I'm going to go ahead and write that function in. So in this case, this would be like our g of x that I'm inserting into the function of f. So instead of writing x, I'm just going to write out this function, and then we continue on with the rest of the function. And if we can, we'll simplify it. So that becomes my new function, which we would call f of g of x, because I've inserted g of x into f. So instead of writing f of x, it becomes f of g of x. Okay, so let's start with the examples. If f and g are functions defined by these two, find the following composite functions, fog and gof. So I just like to rewrite it as whether it's f of g of x or the other way around, just so I know exactly what to insert into it. So this is telling me to start writing the function f, and then when I see an x, instead of writing x, I'm going to write the function g of x. So starting to write the function f, I can see I've got a square root, but then instead of writing x, what I'm going to do is insert the function of g of x. So that would be 2x minus 1. Now for goth, similar idea. I'm going to start writing the function g, and then we come across an x. So instead of x, what I'm going to do is I'm going to insert the function of f. So that'll be root x minus 1. So that's how we would complete composite functions. Now, a question is, does fog work? So we're just specifically looking at fog for every single value of x. Now, we can see that there's a square root here, right? So even though when I initially insert x into here, we know that this is a linear function, so x can be inserted for all of them, there are lots of values that will come out of this that cannot be square rooted. So actually, we have a little bit of a restriction here. So here's an example of what I'm talking about. Let's start off with g of x. So we're looking at f of g of x. And if we start off with x is equal to -5, let's put that in to g of x. So that would just simply be 2 times -5 minus 1. I get -11. So my initial input is -5. I get an output of 11. Now let's see what happens. So remember, with composite functions, your output becomes your new input. And if you think about your output, this is kind of like your y value, right? Because usually that's equal to y. And we know that y is the range. So the y value, our output, the range, becomes the domain of the new function. And we know that we cannot have a domain that is a negative value, because we cannot take the square root of -11. So that leaves us with a little bit of an issue. The fact that this function is actually not defined for every value of x, even though the inside is defined for every value of x because it's linear, this whole function will not be. And we're going to talk about that very soon. Okay, so the existence of composite functions. Here's the general rule that you need to know, and I'll explain why, but you can you don't necessarily need to know why, but I think it is better for you to understand it if you don't, as long as you understand this rule. So the rule is the range of the second function, which we usually call the inside function, is a subset of the domain of the first function, which we usually call the outside function. Now, why is this the case? As we spoke about in the previous slide, remember we initially have an input that goes into f of x, that turns into our output, right? So this is all for f of x. However, we then need to put that into our new function, g of x, which would be the outside, or g of f of x. That becomes the output to give me the input, to give me a new output. Now, here's the problem. If this output, which is the range, does not work as the x value is the domain, then that function will not have an overall output. There will be nothing left for it. So this is what the rule is. The range of the inside needs to be a subset of the domain of the outside, and this is the reason why, because the output becomes the input of the new function, or the outside function. So here it is defined. For fog, or f of g of x, to be defined, the range of g of x needs to be a subset of the domain of f of x. For goth to be defined, then the range of f of x needs to be a subset of the domain of g of x. Also, we have a rule as well. The new domain is always the domain of the inside function. So you'll see textbooks using words like second and first. I just prefer to use inside and outside. It just makes a lot more sense. Here's just a bit of a depiction visually of what we've just spoken about. And I know I'm going on about it quite a bit, but it's a really important part of composite functions here. So first we start off with f of x, which is the inside here. We have some sort of domain, we have an x. What we do is we figure out, when we substitute x, we get a y value. That y value, which is the range, becomes the new domain, because I'm going to input that into my outside function. So the idea you have to remember is that the range becomes the domain of the new function. So if the range is not part of that domain, then the new function is not going to have an overall output there. Okay, so it sounds like a kind of complicated process. So what we're going to give you is a tool to help you to actually complete this. So the existence of composite functions. We have this table, which you'll see I'm going to use it quite often. So in this case, we draw up our domain range and we write f and g. And what we need to do is write out what the domain and range is for both of our functions. Then say we've got the function f of g of x. I'll draw an arrow. As you can see, there's this arrow here to tell me that the range of the inside needs to be a subset of the domain of the outside because the output becomes the input. And so I'll draw this arrow and I'll say, is this a subset of that? If it is, it does exist. If it doesn't, then we have to do something about it. Also, I draw this box because the domain of the overall function will be equal to the domain of that inside function there. All right, so that's all the theory. Let's go ahead and do a few examples, which will hopefully make it make a little bit more sense. So example 6, for the function of g of x is equal to this and f of x is equal to that, state what is defined. Now, in order to figure out what is defined, we're going to draw up our table and we're going to figure out, do the subsets work? So this is f of x, this is g of x. Let's go ahead and work them out. Now, g of x is just a straight line. So for the straight line, the domain is R. For the range, the domain is also R. Sorry, I've written that in the wrong box. Now, for f of x, this is the square root function, which looks like that. So we can see that the domain is going to be from 0 to infinity included, and the range is also from 0 to infinity. Now, starting off with f of g of x, that means because g of x is the inside, the range of g of x needs to be a subset of the domain of f of x. Is that true? No, because all real values is bigger than 0 to infinity. So we'll just start with part A, f of g of x. And the way that we can write it is that all real values is not a subset between 0 to infinity, which is the range of the inside needs to be a subset of the range of the domain of the outside. Therefore, bog does not exist. It's not going to work because what's going to end up happening is a bunch of these values that I get out as my y value, when I input it as an x, they're not going to work. I can't take the square root of a negative number. Now let's go ahead and try for part B. So that's g of f of x. So we'll do that one in green. So now we want the range of f of x, that's the inside, to be a subset of the domain of the outside. Is that true? Yes, it is. This is smaller than all real values. So that is defined. That's for Goff. Okay, so sorry, that's actually part A still. This is part B now. So it says for the composite function that is defined, state the domain and rule. So the one that is defined is g of f of x. So to figure out what the rule is, remember we start writing the function of g, and then whenever I come across an x, I'm just going to substitute in the other function. So it'll look like this, and then we continue. Now the new domain, remember, is always the domain of the inside function. So since we have f of x, the domain will be this one. Okay, we can only put in x values from 0 to infinity, and that makes sense because I obviously can't take the square root of a negative number. Okay, so that's basically how you work out what a composite function is and whether it's defined or not. So our next question is, well, what if a function is not defined? Do we just give up on the question? Absolutely not. We actually need to restrict the domain. We need to do something about the domain to make it work. So again, remembering that the range of the inside function is a subset of the domain of the outside function. So if it doesn't already fit, we need to make it fit. We will just change the range. And remember, the range affects the domain in order to be able to make it fit. So that's our rules, or what we do. Restrict the range. To do that, we need to restrict the domain. So let's try out example 7. So for the function of f of x is equal to x squared minus 1, and g of x is equal to root x, state why g of f of x is not defined, and then define a restriction. So we're going to do the same thing with the table. So we've got f of x, g of x. Now f of x is a parabola. So the domain is just all real values. And the range, it's been dropped by 1, so that'll be from -1 to infinity. For g of x, this is just a square root. So the domain is 0 to infinity, 0 to infinity for the range as well. Okay, now for it to be defined, the range of the inside, so f of x, needs to be a subset of the domain of the outside. And we can see that that very clearly does not fit. So the range, which is from -1 to infinity, is not a subset of the domain, which is 0 to infinity. Therefore, g of f of x is not defined. Okay, it doesn't work that way. So what are we going to do? We need to restrict it. How do we restrict it? So what we want, so -1 to infinity, if I kind of think about it as like a number line, here's -1 to infinity. That's what that one is for the f of x. However, what we want, g of x, would be from 0 to infinity. So this part here is an issue for me. What we want, just get rid of it. So instead of the range from being -1 to 0, what I want is for it to be 0 to infinity so that it matches. So that's the largest range that I can have that actually would work. But as we said, we don't talk about functions in terms of their range. We always talk about them in terms of their domain. So now that I know that I want the range to be from 0 to infinity, I need to think about, okay, well, what will the domain be? What will be the allowed x values? The easiest way, in my opinion, to do this is to sketch it. So I'm going to go ahead and sketch this function. X squared minus 1 should look something like this. So that's -1. This will be -1 and 1. And I'm going to highlight the parts that I do want. So if I want from 0 to infinity for my y values, that means I want all of this part here. I don't want any y values that's below the x-axis. So hopefully now you can kind of see what the actual, what the x values that I will want is. So anything that's highlighted for x, that's what I would want. So from this point backwards and from this point forwards. Anything in between them for an x value will result in a negative y value, which is not what I want. So that is going to become my domain. There's a couple of ways that you can write it. So you can either write that I want from -infinity to 0, and you can include it, that's fine. And from 0, sorry, not from to 0, that was a bit silly, from -infinity to -1, or from 1 to infinity. Or the other way you can write it is that we want every real value except for the values between -1 and 1, not included though, because I do want the values of -1 to 1. Okay, so either one of these will work, but those are the x values that I'm allowed to have in order to be able to get the range that I want, which is all the positive values. Okay, so that would be defining the restriction for it. So to write that out formally, we would say f of x, or rather we can write it as a proper rule. Actually, we'll just write it like this, f of x, x squared minus 1, where x is an element of every real value except for -1 to 1. So something like that, where we have the function and we have the domain written as well. Okay, on to the next example. It says let f of x equal x minus 1, g of x equals x squared, find g of f of x, the domain, and then sketch the graph. Okay, so same kind of idea. First, we're going to check that it actually works. It's always really important. So even if they don't tell you to check whether it's defined, you should still check that it is. So that'll be f of x, g of x. F of x is a linear function. So the domain of that will be R. G of x is a parabola. Domain of that will be R. And then the range for the linear function is R. However, the range for the parabola is 0 to infinity. Now, in order for this to work, the range of the inside needs to be a subset of the domain of the outside. So that's great. That works. You can write something about it or you can just continue, but I'm just going to write range of f of x is a subset of the domain of g of x. The function exists. So that's just to make it very clear to the assessors that you know what you're doing in this case. And so then we can start answering the question, find g of f of x. So I'm going to start writing g. Whenever I come across x, I'm going to substitute in, which I come across very quickly. So that'll be x minus 1 squared. And we need to find the domain of it. Now remember, the domain of this function is equal to the domain of the inside, which in this case is just R. So there's nothing really fancy about this. Okay, that's for part A. Now for part B, it just says to sketch it. So there's no domain restriction, it's just a basic function. It should be quite straightforward. So this is just a parabola that's moved 1 to the right. So that'll be 1, 0, x, y, and it'll also intercept at 0, 1. There's no domain restriction, so it'll just be as is. Okay, next one is example 9. So if f of x equals x squared, g of x is equal to the root of 2 minus x. Find the largest domain of f such that g of f of x exists. Find the rule describing it. So in this case, it's the same idea. It's already implying the fact that it's saying find the largest domain that makes it exist. It implies that it doesn't exist in the first place. So we're going to have to do some sort of restriction. In order to do that, we're going to draw up our wonderful table. So if you don't already have a table in your notes, please draw one up. And you'll notice in the exam, they don't give you a table. You're just going to have to draw one for yourself. All right, so it's probably as good as I'm going to get it here. Not too far with the eraser there. Okay, and we'll usually list domain, range, f of x, g of x. All right, our two functions. F of x is a parabola. So the domain of that will be R, range will be 0 to infinity. And then the second one, this is a square root function that has been reflected in the y-axis and has moved 2 to the right. So that'll look like that. So the domain of this is from negative infinity to 2, and then the range is from 0 to infinity, all positive values. Okay, now in terms of existence, we want the range of the inside function to be a subset of the domain of the outside function. So 0 to infinity is in fact not a subset between, or for negative infinity to 2. You can tell that that's not going to overlap. If you find it a little bit difficult to figure it out, you can always draw it as a number line. So 0 to infinity, here's 0. Let's make that go to infinity. And then 2 for the second one, we want that to negative infinity. So we can see that the lines don't fit within each other. Now, in order to restrict it, what we want is to make sure that they do fit within each other. Specifically, I want to make sure that the range of the inside function fits within this. So I have to cut it off at a point so that it will fully fit within it. So I can see that, in fact, I want this range to become from 0 to 2. It can't be any larger, otherwise it's not going to work. So 0 to 2 will be a subset from negative infinity to 2, but 0 to infinity doesn't work. Okay, so as we said before, we know what we want the range to be. We want it to be 0 to 2. Now, in order to restrict the range, though, we need to restrict the domain. So the way to do that, we're going to go ahead and sketch our graph, highlight the range that we do want, and figure out what's the corresponding x values. All right, so here's my function, x squared. Looks like that. All I want is the values, the y values from 0 to 2. So here's 0, here's 2. So only from 0 to 2 is this function allowed to exist. Otherwise, it won't work. So what my job is to find the corresponding x values. So that'll be x from this point to this point. That will be my domain that I'm allowed to find. To do that, I just need to find the x values. So I know this is y is equal to 2. To find the x value, you can just substitute it into the function. So then that will be plus minus root 2, positive root 2, negative root 2. Therefore, my domain that I'm going to have is from negative 2 to 2. So as long as x is between negative 2 to 2, that is going to give me a range that will be from 0 to 2, which will be a subset. Okay, so then it says find the rule describing g of f of x. So we can write it, g of f of x is equal to, start writing out g. Whenever you come across x, put in f. So that'll be 2 minus x squared. And then we'll also associate or write down the domain. So remember, the domain of the new function is equal to the domain of the inside function. Now we restricted this domain to be from -2 to 2. So this will be the domain of the inside function. Okay, and that there is your rule that is defining your composite function. Okay, that's it for this exercise. So good luck, keep trying. It is a little bit tricky to get your head around at first, but the more that you practice, the better that you'll get at it. See you next time.